searches. So our first speaker that will tell us about data quality is Ronaldas Macas, who is a member of the LIGO collaboration. He's a postdoctoral researcher at the University of Portsmouth, and he is specializing in understanding the mitigation of noise for gravitational wave detector. So I hope I pronounced your name correctly, and enjoy.
Thank you. Hello, everyone. Let me share my screen. Okay. Are you able to see my slides?
Yes.
Perfect. Okay. So let's start. Yeah, hello, everyone. Again, today I will be talking about data quality in gravitational wave detectors. I will start from acknowledgements. So in order to prepare these slides, I was using quite a lot of material from the previous years, just because many things have not changed, some things have changed. So this was really like a team effort. If you want to have a look at these previous year slides, you can actually have a look at this link, and you will see the previous year slides. So today I will be talking about some short introduction about the strain data. So what is the strain data? How does it look like in time domain, in frequency domain, also in time and frequency domain? Then I will be talking more about data quality itself. So what are noise artifacts, what tools we use to inspect the data quality in gravitational wave detectors, and then I will give a brief summary of data quality in O3 and what we can expect from the next observing run 4. And then in the end, I will give quite important references. So firstly, let's start from the basics. What is the strain data H of t? So gravitational wave strain data is really just the relative difference between Lx and Ly arms, which is given right here with this equation. Right here with this equation. And what it actually means, so here is a very simplified diagram of the detector. You basically have laser, you have X and Y arms, and when a gravitational wave passes through, it's going to change the length in the space-time, and because of that, these arms are going to change in distance as well, in length as well. And that is basically just a simple one-dimensional quantity, H of t. So to some extent, you could say that it is a very simple quantity. H of t is just one-dimensional quantity. For example, astronomical data sets are like images most of the time, so they have like 2 dimensions. So maybe this is like simple gravitational wave data, H of t. But well, you can see from this image, so this is raw time series data. It looks quite complicated, at least in my opinion. So you can see that there's, for example, some low frequency stuff happening, like a breathing mode. There's a lot of high frequency wiggles happening, and you're not really sure, looking at this data, is there something important happening with this data? Is there like a glitch if there's a signal? So you're not really sure just by looking at the raw time series data. So this H of t is sampled at LIGO detectors with 16 kilohertz. So that means that for 1 second, you have about 16,000 samples. And then for the open data that you can get on QUASC is 16 kilohertz or 4 kilohertz data. And as I said previously, it kind of looks quite complicated, but then we will do some data analysis tools to see that it can actually be much simplified. So then we have frequency representation of the same time series data. So let's take, for example, 512 seconds of the time series data. And then you divide that 512 seconds into shorter chunks. So for example, 4 seconds. And then you take these 4-second chunks, and then you just do the FFT. So you take a Fourier transform of these segments. And then you basically take the median Fourier transform of these segments. And then this is the plot that you actually get with some additional modifications, but this is the idea. So this is showing you the sensitivity. So that median Fourier transform is actually the median detector sensitivity. And this is how the detector sensitivity looks like. So contrary to like many like intuitive sense, you would think that the higher number is better, but actually in gravitational wave data, the lower number is better. So this is on y-axis, this is gravitational wave amplitude spectral density. I will talk about that in the next slide. But basically, this shows you how much you're able to measure how small difference in the length you're able to measure. So you want to be able to measure as small differences as possible. And that's why you want to have your sensitivity to be as low as possible. And that's looking at this image, you can see that actual gravitational wave detectors are the most sensitive at around like 100 to 200 hertz. Then it is really bad sensitivity at lower frequencies, just because of the ground motion mostly. So you're not very sensitive at those frequencies. And then at higher frequencies, you also get like quantum effects happening. And because of that, you're not very sensitive at higher frequencies as well. It doesn't mean that you cannot extract any information from the detector. It just means that you basically need to be careful at, for example, any low frequency information, because you see that the detector is very noisy at low frequencies. In order to like make more sense of the raw time series data, we actually do the whitening time series. So what does it mean? So first, as I said on the last slide, transforming strain data to frequency domain allows us to estimate the average detector sensitivity for each frequency bin. So we can say that for that particular frequency, we're that sensitive. And this is so-called amplitude spectral density. And having ASD allows us to whiten the data. This is a jargon in data analysis. It is basically meaning the scaling the data. So for example, detector is less sensitive at lower frequencies because of the previous plot that I showed you, and that happens because of the ground motion. So basically that means that any information at low frequencies should be to some extent less important than at medium frequencies. And this is just because if you detect something at low frequencies that is like a very strong signal, you need to keep in mind that there's a lot of noise happening at low frequency, and that noise is also like quite loud. So that's why you should be to some extent scaling the data. And this is how it looks like. So you have this raw time series data, and then you just divide by ASD. Like you use Fourier transform to do that like in frequency domain, but basically this is the result that you get. So after you take this 1 second of the data, so looking at this 1 second of the data, raw time series data, you cannot really see anything suspicious. There's maybe like some strange wiggle right here, but you're not really sure what is happening. Is it important? Is it not important? Yeah. So what you do, you basically divide by ASD. You basically scale the data, and that allows us to get like this plot down that you can see right here. And here you can clearly see that there's a huge excess power happening at like around the middle plot time. Something is happening just in like the first 0.1 seconds of this plot. And in this plot, you can see much clearer that there's actually a huge signal. This is actually not a signal, but a gravitational wave noise, because signals are not really that loud in gravitational wave data. But yes, you will not be able to see that from the data right here. So this is the frequency. This is basically the scaling the data. And then gravitational wave scientists also like to look at the images. And for that, we are using Q transforms. There's a Q transform. It is also called Q-scan, Q-series, spectrogram, omega scan. So multiple names, basically meaning the same thing, that we want to look at the plots of frequency evolution over time. And there are just like a small differences like normalization or something like that. What is a Q transform? So firstly, you select a Q value, and Q value is defined by this equation, which basically means that you select a frequency, central frequency, and then you divide by bandwidth. So this is a representation of how the Q tiles look. So for example, if you have a low Q value, for example, 8, then you're good at short duration signals that have huge bandwidth. Or if you, for example, have high Q value, for example, 100, then you have long duration. Then this type of a tile is very good for long duration signals like binary neutral source signals. For example, from yesterday's tutorials, you were using, I think so, 110 Q value to plot Q scans for the BNS signal. That is because the BNS signal, the in spiral part, is very long, and that's why you want to use like this type of tile rather than like this type of tile. So yes, so you basically select the Q value, you select the tile essentially that you want to tile your time frequency data. Then you find the most optimal value, and that is really subjective. So it really depends whether you're looking at short duration signals, at long duration signals, and so on. And then you basically make a Q transform plot for this particular Q value. And this is how a plot like this would look like. So you can see that it allows us to see the frequency evolution of the signal over time. And that is very important because like all of the gravitational wave signals basically have some sort of frequency evolution over time. And it is much easier to look at this type of plot than at frequency domain or like time series domain. So this is a very important plot that we are using quite a lot in data analysis and in data quality as well. Now let's have a look at the data quality. So gravitational wave noise, contrary to many searches would think. So in many searches, there's this assumption that gravitational wave data is Gaussian and stationary. But actually, in my type of work, when I'm working with gravitational wave data noise, I can see that the data is actually non-Gaussian and non-stationary. So that means that there's a lot of noise that is changing over time. There's a lot of noise that is actually like very loud, and it is sometimes even similar to gravitational wave signals. And these that noise we are calling glitches. And here on the right-hand side, you can see different type of glitches. So you can see there's like a huge range of glitches. There's like actually many more type of glitches than what you can see here. But you can see that, for example, we have like short duration, high bandwidth glitches, which are actually called blips. Then you have like long duration and small frequency bandwidth signals right here, or for example, like really messy glitches like that one. So there's really like a huge range of glitches in gravitational wave data. And why should we even care about those glitches? Well, firstly, they affect gravitational wave detector sensitivity. So, for example, if you have a glitch like this, you can actually see or try to detect anything, and that really affects the gravitational wave detector sensitivity. It also affects gravitational wave searches. So, for example, this sort of a glitch, which is so-called blip glitch, it is very similar. It looks very similar to a gravitational wave signal, a binary black hole signal that is very massive. And because it's a very massive deep-based binary black hole signal, it is going to be very short signal and high frequency bandwidth, which basically is looking very similar to this glitch. So that's why gravitational wave searches get confused when they see this sort of a glitch and they think that maybe this is actually a signal. So they can affect gravitational wave searches. And also these sort of like glitches can also affect the parameter estimation. So for example, sky localization. If you're trying to send astronomers the sky localization of a gravitational wave event, you want to have the sky localization as precise as possible. But if there are glitches nearby, some glitches like that, next to a signal, it can affect the sky localization of the gravitational wave signal. So that is quite important, not only from our gravitational wave perspective, but also for other astronomers as well. So how do we detect the glitches? It is quite easy to detect glitches just basically because what is a glitch? Essentially, it is basically a glitch is something that is non-Gaussian. And this is what is basically used in this tool, Omicron tool. And it is we have been using that for years. And here on the right-hand side, you can see a plot of for 1 day. And basically these all small dots are basically glitches at different frequencies. So you can see, for example, that there's a lot of glitches happening at 40 Hertz for that particular day. Then something was happening at this particular hour, about like 8 hours UTC time for this particular date. So this is from the third observing run. And then you can see that, for example, there's a lot of glitches just like before the lock loss at around like 20 hours. And this is actually scattering glitches. These are like low frequency, many glitches. And then there's like a lot of not very noisy, but a lot of glitches at high frequency, but we shouldn't really care about them because, like, as you remember, the sensitivity is not very good at those frequencies. And these glitches are not really that strong. But you can see that there's like a lot of glitches that are happening during the day. So there's really like thousands of glitches that we record every day. And then another important and interesting thing is that glitch rate varies over time. So this is the plot showing you how the glitch rate changed over time. So for example, for LIGO Hanford detector, you can see that this is like in the second observing run, the glitch rate was something about 0.1 glitches per 1 minute. But then, oh yeah, so it doesn't actually tell the exact, glitch rate per minute. Yeah, exactly. Yeah, so about 0.1 glitches per minute. And then you can see that in the third observing run, it actually increased the rate of glitches. And then also you can see at the x-axis, so this is time days from April. So this is for the third observing run. It actually changes over like, months of time, for example. So sometimes, like, for example, LIGO Hanford is sensitive to like ocean waves or like winter times. because of the seismic noise, and because of that, it can have like some noise right here. So yeah, so there's like a lot of factors causing these glitches, but it changes over time, and then it changes for each observing run, as you can see. So for LIGO detectors, you can see that the glitch rate actually increased quite substantially by factors of like 3 to 5 from second observing run to third observing run. But then for Virgo, we can see that it actually decreased quite significantly. And this is because Virgo detector made some important improvements in the how they are hanging their mirrors, and because of that, they were able to reduce the glitch rate quite significantly. For LIGO detectors, that was done previously, so they didn't have that issue in the second or third observing run. So yes, so it is important to keep in mind that glitch rate varies over time. It changes from each observing run, and it also changes for each day, essentially. And what is the origin of these glitches? So we know some origin of some glitches. We cannot really know some origin of other glitches. So for example, there's some glitches that are caused by natural things, for example, like thunderstorms. And here on the top, you can see an image of a scat of the thunderstorm glitch. You can see that this is basically just a wideband glitch happening over a period of like a thunderstorm, essentially. And then there's actually some human-made. So, for example, there are trains that are driving past Livingston detector in Louisiana, and that is causing like some glitches, and that is causing some problems, of course. Or for example, like really like very funny ones, like for example, a fridge connected to the main power, and it can cause like, some glitches as well. So we have like natural and human-made glitches, and then some glitches are actually recorded by witness channels. So for example, I will talk about that later, but we also have like a lot of sensors around our detectors that are trying to record a lot of things, and maybe we are able to basically find the origin of the glitches. So we know that some glitches are recorded by our sensors, and we know that what is causing them, but then we do not have information about some other type of glitches. So for example, light scattering glitches, they are called light scattering glitches because, well, we know what is causing them. It is caused by light bouncing from in the beam, and we found that by looking at the witness channels. But for example, blip glitches that I'll show you later, we do not really know what is causing these glitches. So yeah, it is not really clear-cut thing for glitches. For some glitches, we know what is happening. For some other glitches, we do not really know what is happening. Good thing about some of these glitches, when we are able to identify what is happening, what is causing these glitches, we are able to mitigate these glitches. And this plot actually shows quite well what was done in the third observing run for LIGO detectors. So we basically implemented RC tracking, which is basically used to reduce these type of glitches. And this is basically the plot showing the SNR of these glitches before the RC tracking implemented, and then after the RC tracking was implemented with the red line. So, and this is SNR on x-axis and number of triggers on y-axis. So you can see that basically after implementing RC tracking, we were able to reduce the SNR of glitches and also to reduce the number of triggers. So that was basically helping quite a lot. What tools do we use to inspect the data to try to find the glitches and try to mitigate those glitches? So firstly, we basically following this sort of procedure. So we want to get rid of glitches, but how? So firstly, we need to identify the noise. Then we need to look for potential correlations with the witness channels that I'm going to talk about that later. Then we need to perform multiple tests to simulate that noise to make sure that this is actually causing the noise. And then we are trying to fix the noise source, or if we cannot fix the noise source, we can try to reduce it or maybe mitigate it. And then if you are not able to eliminate the noise source, or we cannot like mitigate that noise source, you can try to model the noise or create videos. And for all of these steps, we are using multiple tools. So in our analyses, we are using Omicron, Q-transform. So I talked about these tools, and then I'm going to talk about Gravity Spy, HV2, and a couple of other things. And basically, these first tools we're using for identifying the noise. So Omicron, Q-transform, and Gravity Spy is used for identifying the noise. And then HV2 is used for looking potential correlations with the witness channels. So let's talk about Gravity Spy because I haven't talked about that. So Gravity Spy is actually quite interesting tool. So this is an image recognition algorithm based on machine learning. And it is able to classify chance and noise. So it is able to classify these type of glitches in 23 classes. It is not actually naming those glitches. It is just giving the classes. And then we humans tend to name things. So that's why we are calling these glitches as they are shown right here. And basically, this algorithm is trained on the time frequency spectrograms of the noise transients. So really just like these Q transforms. And then for the input, we're using Omicron triggers. And then for the output, we're saying that please classify these glitches in like 23 classes, for example. And here you can see that basically it is able to classify these type of different glitches, and then humans just name them. So this is how a blip glitch looks like. So this is, as I said, like very short duration and high frequency bandwidth glitch. And this really represents like a high mass binary black hole event. Then Tomty glitch is basically something very similar to a blip glitch, like it is relatively short, but a bit longer in duration, and then relatively high bandwidth. And then, yeah, like we have different type of like scatterings, fast scattering and slow scattering, and this is called by light bouncing from the beams in the gravitational-wave detector. And then there's like some whistles and puffish and so on. So yeah, so basically this tool is very useful. And actually, yeah, you can have a look at this publication. But this is so-called like public citizen science project. So even you, as a volunteer, you can actually go to Gravity Spy database and try to help to decide which glitch is which belongs to which category, and you can try to improve the data quality yourself. So I would definitely recommend to go and have a look at Gravity Spy and see if you would like to contribute. And then you have witness channels. So gravitational wave detectors have thousands of sensors that record various activity. And if you remember the first image that I showed, the very simple image of the detector, this is a bit more complicated image. This is still like very simplified image, like there's like way more things happening, but this is a bit more complicated image, but still very simple. And I'm not going to talk about this diagram in detail, but essentially the idea is that here is the laser, here's the beam splitter, here are the mirrors in the X arm and Y arm, and here's the detector, photodetector, and there's a lot of things happening. And basically we have like each of these, like for example, each mirror is suspended on like four different suspensions. And each of these 4 different suspensions have like basically dozens of sensors that are sensing how these mirrors are tilted, what is the acceleration in these mirrors, and so on. So basically we have a lot of sensors in the detector. We have like a lot of sensors outside of the detector that is able to tell us what is happening in the detector and outside of the detector. And these are so-called witness channels. Why that is useful? Well, it is useful because we can use those witness channels with hierarchical veto, which is so-called H veto. So what we do, we basically just take statistical correlations between noise and gravitational wave strain channels, so H of t, and then we look for statistical correlations with these witness channels. And this is basically the table that we get with this H veto. So for example, in this particular day, we found that this particular channel was statistically correlating with the strain data the best. And this is so-called like L1. So this is like Livingston lens and sensing control channel, which is called like that basically. And then if you go to the previous documentation, the previous spot, this is the channel right here. So LSC Ruffle A. So you can actually go back to this diagram and see that basically this noise that was happening on that day was statistically correlating mostly with the H of t, which was basically happening at this part of the detector. So then people would go back to the detector and they would try to see what is happening with the detector at this particular site and try to see if we can basically mitigate the noise, or maybe something is happening wrong with this part of the detector, and that allows us to basically mitigate the noise. And yeah, so that allows us to find the potential noise culprits, and we can try to mitigate those noise sources. But that does not work all the time. It works quite often, but not all the time. Just because some noise sources are not recorded by any witness channels, like as I said, for blips, we still do not really have a good potential channel correlating with this with blips. And then with many other sources, we're not actually able to like record that noise well enough. So this is H veto. So as I said, quite often we cannot really find the root cause of the noise. And for that, we can try to use the noise modeling to try to remove the noise. So when we cannot like try to mitigate that, we can try to remove it. We can try to model and then remove it. For example, here we can see one of the gravitational wave signals from the last observing run. So here's a binary black hole signal. And then there was some noise happening after the signal, and actually there was some noise happening at the signal as well. And we had one witness channel, which is just called like a radio frequency 45, essentially. That is just like one single witness channel. This is basically the plot at the same time axis as this plot. And you can see that we can see like a glitch or like excess power right here. And this is what's happening with H of T. You can see there's some excess power in this witness channel recorded, and it is also happening right here. And there was actually some noise happening at this particular time during exactly when the signal was happening as well. So during that astrophysical signal, there was some noise recorded in the witness channel. So we can actually try to use linear noise subtraction to try to model this correlation, and we can try to remove this noise. So for that, we are using linear noise subtraction, which was like developed a couple of years ago. And we can use this witness channel information to model the noise in H of T, the gravitational wave strain data, and then we can try to remove it. So this is the original data, just a shorter segment. So this is the astrophysical signal, and this is the glitch. Then we can basically model the noise and remove it. And you can see, for example, that after cleaning the data, we do not really have the glitch right here anymore. So it basically works quite well. And then you can see that basically there's the residual. So this is the data that was basically taken out. But unfortunately, we cannot do this quite often because most of the times we are not able to find the auxiliary channel, the witness channel for this type of noise. So instead of that, we need to use Basewave. And Basewave is basically able to do some fancy modeling of the noise with some prior assumptions. But basically, it is using like wavelets to model the noise or like maybe model the signal as well. And for that, we are not using any witness channel information. So for that, like for example, here's the examples. We have like a gravitational wave signal right here. There is some noise happening right here, and then we can actually use Basewave to subtract the glitch. And this was what was subtracted. So we are able to remove some part of the noise, not everything, but we are able to remove some part of the noise. And then if nothing else really works, we can create data quality vetoes. So that basically is saying that we cannot really find the noise source. We cannot really model the noise itself. So what we can do instead, we can basically say that, look, don't use this data, or like use this data at that particular time and be very careful of that. And that's so-called vetoes. So these vetoes basically have different categories depending on the seriousness of the issue. So the first category of vetoes are basically meaning that there was a major issue with the key detector component, and you should not use that data basically almost never. Then there's category 2, which is basically saying that there's no noise, there's a known cause noise coupling to gravitational wave strain H of T, for example, high ground motion. So you can try to use that data, but you should be careful. And if there's like a signal that you detect, you should be basically looking at that further to see if that is not caused by noise. And then category 3 is statistical noise coupling to H of T that is not really well understood. So basically we have like H veto. We see that there's like some noise that is coupling quite well to the gravitational wave strain, but we can actually see why that is happening, and we do not really understand why that's happening. Then in Gravitational Wave Open Data Science Center, you can find basically these flags for each of the observing run data. And then the last link that I wanted to show you is basically daily detector status, and you can click on this link later when you get the slides. But this basically is a public page that is showing you the status of the detectors for each date when they were operational. So for example, this is particular date for the BNS event, for binary neutral star event 170817. And for that particular date, you can see the sensitivity curves for this particular date. You can actually go and have a look at this page for today, for example. Detectors are not all of them are turned on, but like you can see what is happening with the detectors at the moment. So you would be able to see the sort of a plot for like detectors if they are operational. Then you can also see basically operating segments data. So for this particular date, Hanford, Livingston, and Virgo detectors were working quite well. And the BNS event happened, I think so, at around this time, at around 1 p.m. UTC. So all of the 3 detectors were operating, and GU, I think, so was not operating at that time. I'm not really sure. And then there's another important plot, which is basically showing that binary detectors are in spiral range, which is basically showing you the sensitivity of the detectors. And at that particular date, the Livingston detector was about 100 megaparsecs, Hanford detector was about 50 megaparsecs, and Virgo detector was about 25 megaparsecs for that particular date. And then you can have a look for example, what is the sensitivity of detectors today, if you want to. In 03, we had 12 months of total data, or like 11 months of data taking. During that third observing run, we detected 74 gravitational-wave detections in total, and then actually about 24% of them required glitch mitigation. That meant that basically 1 in 4 signals usually had a glitch nearby, and that meant that we basically had to use phase wave or like linear noise subtraction to try to model and remove the glitch. And then, just because I think so I'm running out of time, so I will not talk about these images, but this is just basically showing you the sensitivity range and which detectors were turned on for how much time. Then talking about 404, so the 4th observing run is planned to start in basically a week, like next Wednesday. And what is, I think, so quite important, so here you can see at the right-hand side the planned sensitivities. And you can see, for example, that for LIGO detectors, we are planning to start from about 160 megaparsecs, and we finish with about 130 megaparsecs in 03. And that does not seem really much. Like, for example, if you divide by sensitivity, you basically see that there was about like 20% increase in sensitivity, which is not really that much when you think about that. But then you need to keep in mind that basically 20% more sensitivity means that you have about that is your like range, but your actual observed volume goes to the cube of that. So because of that, like 20% more sensitivity means that you're basically getting almost like double more signals. So that means that there's a huge influx of like additional detections. And in order to achieve this additional sensitivity, there were multiple things that were changed. So we tried to increase laser power. We also tried to remove low noise sources that you saw at lower frequencies. Then we also installed like new mirrors because there were some problems with the previous mirrors. And then we also added frequency dependence squeezing, which is like a very complicated topic. I'm not really expert in that as well myself. So there's a reference later on that. But yes, we basically made a lot of changes to the detectors to basically be able to have that 20% increased sensitivity. And then I will leave you just with data quality references. So about LIGO strain data, there's a couple of important and interesting papers about strain data, and then about LIGO data quality. There's like one of the papers that talks a lot about the data quality itself in the 2nd and 3rd observing. So this is excellent paper if you want to have a look in more detail what is happening with the detector. And then just a couple of other extra papers about what I talked previously, for example, like frequency dependence squeezing. So these are the papers, and that's it. Thank you.
Thanks, Ronaldas. Very nice talk. Was very, very clear. So in ask.igwin.org there are many questions. But there have been a lot of activities. Thanks to all our mentors that have replied to the questions, more or less. But maybe we have a few minutes. Is worth discussing some of these questions. So, for example, one of these ask, what are the reasons behind these glitches? How trains and fridge connected to the main power creates glitches?
Yeah, so let me go back to these things. Yeah, for example, slow scattering. So when the train is passing by the detector, I never been to Livingston detector actually, but I know that there are trains nearby the detector. So when the train is going by the detector, it shakes the ground. And because the ground is shaken, the beam, like the beam tube, like the laser itself is also shaken. And because of that, you basically get this scattering, light scattering, that is scattering from the beam. And because of that, you basically get that extra light in the beam itself. And because of that, you basically get these glitches, which are shown right here. So slow scattering and fast scattering is happening because of the light, because of that extra light. And that extra light is happening because there's that extra movement of mirrors, and these mirrors are moving because of the ground is shaking because of the trains. So this is one of the examples of how trains can affect, how trains can create glitches and affect data quality. For fridges, fridges are basically fridges like in Hanford detector, for example, like you can read basically explanation right here. You can go and have a look. But the idea is quite simple, that basically fridges are like, sometimes they're like, turned on because they need to freeze, and sometimes they're turning off. So accidentally that glitch, that fridge was connected to basically the electrical power that is basically connected to the detector itself. And that meant, for example, when the fridge was powering up, there was also power taken from like the mains. And because of that, you could actually feel that electrical difference in the electrical systems that was used for the detector. And because of that, you could see glitches happening like every 2 hours, for example. So there are like multiple reasons how you can create glitches, and there's like thousands of reasons, but these are just like a couple of examples.
Yes, thanks. So maybe another question, even if it was already fairly discussed, someone asking if there is a register of glitches in the public data. Can I find glitches in the same way I could find events in the tutorials?
Yes, there is. So, for example, if you would go to Gravity-SPY database, I do not have the link here, unfortunately. I should actually put that. So if you could put that question on Ask Igwin, I will reply to the correct link for that. Or basically you can just use like search, like Google search, and just look at Gravity-SPY database. And you would be able to find glitches for all of the open data. So for the first, second, and third observing runs, you can go and have a look at the Gravity-SPY database and say, for example, that you want Tom T glitches or you want whistle glitches. And you can select like different, different times, different signal to noise ratios, and so on. So yes, so this is public. If you cannot find this link, please just try to look. Please post your question on the Ask Igwin, and I will reply with the link.
Yeah, yes, it's on Ask Igwin. And by the way, I think so. It's a Zenodo link, the one we're mentioning, and in the years these links always get updated. So we have everything until 03. I think. So there is a question in the last question in the chat. Does earthquakes or underground nuclear explosion cause noise in the data?
Was the question about earthquakes or nuclear explosions? Like, could you repeat this question?
Does earthquakes or underground nuclear explosions cause noise in the data?
Oh yeah. Earthquakes definitely, and earthquakes is a huge problem. And even, for example, if there's an earthquake happening in Japan, for example, or like somewhere else in the world, we can feel it, and sometimes it's actually causing a lot of problems for us. So earthquakes are like, well, that is basically when the ground is shaking quite a lot, and sometimes this is causing the log loss. So, for example, if I would go to this spot right here, like basically a log loss means that detectors are not observing anymore. And this happens because of the major incidences with the detector. Well, not major, but basically something is bad happening with the detector. So, for example, if there's an earthquake, the ground is moving, and we're not able to keep the detector stable anymore. And because of that, we basically lose the interferometer. We basically just like, we are not observing anymore. So earthquakes are really a huge problem. I'm not really sure about nuclear explosions because I do not know if they are still happening. Well, I don't think so they're happening anymore, but I'm pretty sure if there would be a nuclear explosion, I think so we would be able to feel that with the detectors as well, because like they're very good at detecting seismic motions. So I think so we would be able to feel that, unfortunately.
Yes, and I don't know about LIGO, but about, since I'm Virgo part, I know that there was a paper about earthquakes, trying to connecting our loss of lock with all the earthquakes in the world. So there are studies about the impact of the earthquake, not so much on the noise, but as you said, for us it's another problem. We lose the lock, so it means that the interferometer doesn't work anymore. Okay, so I think we can thank our speaker, because it's about time to go to the next